And I'm recording. Right. Three identical 5K ohm resistors. You put 4 in each one. There are 4 ways to configure 3 resistors, and you didn't calculate the net resistance of any of them. Yeah? You should be able to produce 4 different net resistance values with 3 5K ohm resistors. So, no homework questions, huh? Well, my day just got a lot easier then. I do want to go back and take a little more time going through this charging and discharging of a capacitor. Look at the voltage as it develops across a capacitor. When it's in series with a resistor. Be V sub naught times 1 minus E minus T over RC. And I told y'all RC, the resistance, times the capacitance, is called, represented by the Greek letter tau, it's called the time constant. Now, let's look at some specific examples. When T, get out your calculators. When T is equal to RC, 2RC, 3RC, 4RC, and 5RC. Now, when T is equal to RC, negative T over RC equals negative 1. When T over is 2RC, negative T over RC is minus 2. Similarly, we get minus 3, minus 4, and minus 5. In other words, when T is at 1 time constant, 2 time constants, 3 time constants, 4 time constants, and 5 time constants. At each of these cases, what is E to the minus T over RC equal to? Well, E to the minus, you know what? I'm going to add in one extra one. What happens when T is equal to 0? And that's minus 0. Well, if T is 0, then E to the minus 0 is what? No, E to the 0 is 1. When T is equal to RC at 1 time constant, now E to the minus 1 is 1 over E. or 0.37. Just stick to 2 decimal places would be good. At 2 time constants, e to the minus 2 0.14. Now, e to the minus 3 0.05. E to the minus 4 and e to the minus 5 0.01. Yep. Now, at each of these, what is 1 minus e to the minus t over rc? 1 minus 1 is 0. 1 minus 0.37 would be, what, 0.63? Okay. Now, that tells us, this column here tells us how the voltage is going to increase as it goes across the capacitor. If we have, this is of course if you have a such a circuit like that. The voltage across the capacitor is V sub naught times 1 minus e to the minus t over RC. And the voltage across the resistor is V sub naught times e to the minus t over RC. So, at t's equals 0, the voltage across the capacitor starts off at 0. Goes up like that. At the same time, what happens to the voltage across the resistor? When you turn it on, it spikes up to there when the current flows. Wait, am I drawing that right or am I drawing that backwards? Yeah, it goes concave, not convex. Because it asymptotically approaches 0. It never quite gets there. That one asymptotically approaches V sub naught. It doesn't quite get there. But it continues to get closer. That one keeps getting closer to 0. And if you add this voltage to this voltage, or this one here, they will always add to V sub naught. That's Kirchhoff's voltage law. Now, you did. No, I've never seen it drawn that way, but you found it. That's it. You got it. That's all four of them. And I'd have to do the arithmetic, but I think you got the right answers too. You certainly wrote the equations correctly. Now, notice what happens here. Well, in fact, this is simply 1 minus that. So in every case, when you add these together, they're going to always sum to 1 every time. Now, let's use some specific examples. Let's see if we can, surely they did some specific examples in the book here. Okay, yeah, they give us an example of 1912 of a 30.3 microfarad capacitor with a 20,000 ohm resistor. So, what is the time constant? Somebody? 541. Here, the time constant is what? It's the product of the capacitance times the resistance. So what capacitance are we writing? Do I write here? 0.3 microfarads, or 0.3 times 10 to the minus 6 farads times 20 times 10 to the 3 ohms. What does that equal? .006 is our time constant. That's A. That's the first thing they ask. What is the time constant? Oh, and said the battery is 12 volts. So V sub naught is 12 volts. What is the maximum charge the capacitor can hold, can acquire? The limit. Q is what? No. We're not there yet. What is Q? The charge on a capacitor. Yeah, it's the voltage times the voltage on the capacitor times the capacitance is the charge on one plate of the capacitor. Be 0.3 times 10 to the minus 6 times 12. right? 4 microcoulombs. Is that to 2 significant digits? It's 4.0. We got 2 significant digits everywhere. 0.3 E minus 6 times 12 volts. Yeah, that would be, to 2 digits, that would be 3.6. Yeah. Now that's the maximum charge that capacitor could possibly get in this circuit. The question is, how long would it take it to get that much, to get that full charge? We'd have to find T. Well, it will have 3.6 microcoulombs when the voltage across the capacitor is equal to 12 volts. So 12 volts equals 12 volts times 1 minus e to the minus t over RC. That means this has to equal 1, which means e to the minus t over RC has to equal 0. So when will 0 equal e to the minus t over RC? Devin. If that's equal to 0, this is the same as writing 1 over e to the t over RC. That equals 0 when e to the t over RC equals infinity. When e to the t over RC equals infinity, which means when t over RC equals infinity, then it will have the maximum, the full 12 volts across the capacitor. And since RC is a constant, it would happen when t is equal to infinity. In other words, it would take an infinite amount of time for the capacitor to ever fully charge to this limit of 3.6 microcoulombs, which obviously cannot happen. And that's why it can't happen mathematically. Like I said, the voltage approaches V sub naught asymptotically. Okay? It gets closer and closer and closer to that value, but it never actually reaches it. Never quite gets there. Now, what does that tell you? What does that actually mean? It means that you can pick any finite value of charge, any finite quantity of charge that is less than 3.6 microcoulombs. You can get as arbitrarily close to 3.6 microcoulombs as you would like to, no matter how close you want to get. If you want to get to within 1 times 10 to the minus 10 bajillion, if you've got a calculator that'll hold that many zeros, you can calculate how long that would take. But you will never, you can get arbitrarily close to that value if you are willing to wait long enough. But you can never get to that value. Do you understand what that means? What I'm saying? Okay. So let's work a different example. 6, I think. Page 941, 540, 541. How long will it take you to get to 11.9 volts instead of 12? Now, there's a finite calculation that you can actually do. 11, say again? Divide both sides. Yeah, let's work through this one step at a time. What's 11.9 divided by 12? There we go. Now you subtract 1 from both sides. Eight, 3, 3, 3, 3, 3 repeating. And that equals minus e to the minus t over RC. Okay, well, we can get rid of the negatives since they're both negative. When is that equal to e to the minus t over RC? What if we take the log, the natural log of both sides? That's right. We take the log of both sides and we get minus 4.78749 is equal to minus t to the RC. Well, we know the time constant RC is what? We figured that out a minute ago. 0.006. Right? That gives us minus 0.0287 equals minus t. We can get rid of the minuses. That many seconds, that's 28.7 milliseconds. So if you put a 0.3 microfarad capacitor in series with a 20,000 ohm resistor, it'll take you 28.7 milliseconds to go from 0 to 11.9 volts. Everybody see how that problem is done? Now this has all been talking about charging. We're charging this capacitor. In other words, when we start off with the voltage across the capacitor at 0, and the switch is closed at t equals 0, how long does it take? What happens? The current begins to flow, and this builds up a minus Q here and a plus Q here. And as the electrons flow in, it creates the charge on both plates, and it charges up. The more it charges, the less the more voltage builds up across here. As more voltage builds up across here, less voltage is left to drop across the resistor. With With less voltage across the resistor, the current flows less, and the current slows down as the voltage across the capacitor increases and the voltage across the resistor drops. The current never actually gets to zero, for the same reason you can never get to the full 12 volts. No matter how far you go into the future, no matter how long of a time t you wait, there's still going to be a finite little tiny bit of voltage left across this resistor, which means there's going to be a tiny little finite bit of electrons continuing to flow. How can I make that more intuitive for you? How many of you remember that riddle from when you were kids? If you start 2 feet away from the wall, you step halfway to the wall every time. How many steps will it take you before you reach the wall? Never get there, because you're only going halfway every time. That's what's happening here. So no matter how long you wait, you're never going to get there. You can get arbitrarily close if you wait long enough, but you'll never get there. So this current never actually falls completely to zero. If this ever did fully charge, then it would. But it never will. So, what happens then? That's a defective cup. What happens once it's and let's see, remember the I guess I needed to erase that. Remember the lab circuit we did yesterday? You then put a second switch here to discharge it. Now, it's important to notice that we're discharging it through the resistor, okay? We're not just shorting across the capacitor. But if we open this switch and then close that one, then what happens? This current starts to flow back around through that short to discharge that capacitor. Now, this is these are the equations that describe the charging, how the voltage builds as the capacitor charges. When you turn it around and start discharging it, the voltage across the capacitor now is equal to V naught, which is its initial voltage, times e to the minus t over RC. It's the voltage across the capacitor that's decreasing now, not the voltage across the resistor. And while it's discharging, the voltage across the resistor will be that. Of course, that's only while it's discharging. Once it does discharge, then the voltage gets dropped across the open, as it discharges, the current stops flowing, so the voltage across the resistor is not going to go up to some high value and stay there. You're going to get a spike, and then it'll drop to zero when the current stops. Okay? Otherwise, you just invented a virtual machine, a perpetual machine, where you get free energy for nothing. But without regard to this one, to the voltage across the resistor during discharge, because that's only going to be a spike and then it's going to fall off to nothing. Voltage across the capacitor is going is going to discharge in the same way. Now, any questions about this? No? Any questions about any of this? All right. Well, y'all ready to start your weekend? Okay, well, then. Now, don't you know I could put you on the spot real quick. And I said, well, in that case, let's start chapter 20. No. Now's a good place to start the weekend from. We'll pick up on Monday with chapter 20 in magnetism. So when you finish your homework assignment and get it all ready to turn in on Monday, go ahead and read chapter 20 or look ahead into it and start getting a handle on where we're going from here. You should have just turned it in.
Well, I mean like another one.
No.
Because I know at the beginning you had.
Yeah, and then we took another through the second chapter, and then this one covered what, 2 chapters?
I was just saying.
And I thought I was in politic. You got a whole class of students getting ready to start taking you out front.
That's why I quickly was like, that's just me. Nothing. That's how I didn't for them.
Say again? Yeah. That's the exam that you're supposed to take on Monday. The one you just turned in. Yeah, it was originally scheduled for Monday, but you can let your window down now. I wonder how many people nowadays have no idea what that means to roll down a window. Have you ever thought about, hey, Spencer, have you ever thought about how many young people today have no clue why we call it hanging up a telephone? You used to literally hang the receiver back on the. Nope. Remember those big long 20-foot curly cords? Yeah, that way you could, those curly cords that get all twisted because your mama had to be able to keep it when she went in the kitchen doing her dishes. There are actually people, I've seen people, I have actually heard your age, a kid ask, why do we call it hanging up when we just push, push the button? Yeah. I actually have an idea for a project I want to do for coding I work on. I want to get a smartwatch and do one of those and do the app for the different faces of the smartwatch to show the different time. Because I've got one I want to do that's a 3-dimensional optical illusion. It makes it look 3D. But instead of a watch face, have a 3D image of a little sundial with a shadow. Yeah, it would actually be kind of cool. That and a pile of other things that I want to get to someday. Uh-huh. Yeah. Y'all have a good weekend. See you Monday.